everyone. Thank you for being here today. My presentation is about heuristic construction, a concept under MTES 1142, Computational Thinking in Mathematics. This topic is all about how we can use heuristic strategies, the SMART rule of thumb methods, to solve mathematical problems, especially when standard methods are not immediately obvious. I'm Fatma Azhar binti Razli from class MT2 PPISMP 2429. So let's get started.
Here's what we will cover today. First, we will define what heuristic construction is. Then we will explore heuristic problem solving through easy, intermediate, and advanced level questions. We will conclude with some key takeaways and references. To begin, let's understand what heuristic construction means. According to Merriam-Webster, a heuristic is a method that serves as an aid to learning, discovery, or problem solving. It often involves experimental approaches like trial and error or rules of thumb. In math, this means we approach problems using experience-based techniques such as making lists, guessing, and checking, or simplifying the problem, especially when there's no straightforward formula. Let's begin with an easy level problem to understand how heuristics work in practice. Let's begin with a real-life example. You're planning a small party with a budget of 20 ringgit. You want to buy chips, which cost 4 ringgit each, and cookies, which cost 3 ringgit each. You must buy at least 5 snack items in total. So here's the challenge. What are the combinations of chips and cookies you can buy without exceeding your 20 ringgit budget?
To solve this, we use a heuristic method called make a list. First, we define the variables. Let C represent the number of chips and K represent the number of cookies. The constraints are C plus K must be at least 5 and the total cost for C plus 3K must be less than or equal to 20. Next step is we have to list all possible combinations. Then we create a table to try out all the possible values. For example, if I choose one chip and four cookies, the total is 16 ringgit. So we calculate all the possible values and all of these combinations meet the requirements. By listing out all the possible values systematically, we can easily identify which combinations work. So we have three computational thinking applied in solution 1, which is first decomposition, breaking the problem into budget and quantity constraints. The next one is pattern recognition, which is noticing that as C increases, K decreases systematically. And the last one is algorithm design, which is creating a step-by-step process to list and check combinations. By solving the same problem with a different heuristic, which is guess and check. With this approach, approach, we make a smart guess and check if it works. If it doesn't, we adjust our guess and try again. Let's say we start with 3 chips and 3 cookies. That's 3 times 4 plus 3 times 3. Then we get 21 ringgit. That's over budget, so let's adjust it. So we can try 2 chips and 3 cookies, which is we get 17 ringgit. That works. Let's try another one. We can try 1 chip and 4 cookies. We calculated and we got 16 ringgit. Also works. So the benefit of guess and check is that it can be quicker in simple problems and allows room for flexibility. It doesn't always give you every option, but it helps you find a solution fast, especially if you're under time pressure. We also have 3 computational thinking that apply in solution to also. The first one is decomposition, split into cost and item checks. The next one is pattern recognition, which is notice that reducing C lowers cost more than K. And the last one is algorithm design, which is iterative guessing with refinement.
Intermediate level heuristic question. Planning a study schedule. Now, let's try a slightly more complex situation. Imagine you have to study for 3 subjects: mathematics for 4 hours, science for 5 hours, and history for 3 hours. You have 3 days to prepare, but you can only study for a maximum of 5 hours each day. How do you organize your time?
Our first heuristic here is to draw a diagram. Let's use a table to map this out. For example, on day 1, 2 hours math, 3 hours science, total 5 hours. On day 2, 2 hours math, 2 hours history, total is 4 hours. And last day is day 3, 2 hours science and 1 hour history. The total is 3 hours. The total is 4 hours math, 5 hours science, and 3 hours history. Everything is covered and no day exceeds the 5 hour limit. So that is the final schedule. The intermediate city concept in solution 1 is the first one is abstraction, which is focusing only on hours and days, ignoring other factors like difficulty. The next one is decomposition, splitting the total hours into daily allocations. And the last one is algorithm design, which is using a table to systematically assign and check hours. The second heuristic is work backwards. We could start from the last day. If on day 3 we study 3 hours of history, then the remaining hours is 9 for day 1 and 2. The next step is we have to assign day 3. So we could use the history hours. So the history is finished. Then assign day 2 and day 1. Then we should verify it. And the final answer is day 1 science 5 hours, day 2 math 4 hours, and the last day is day 3 history 3 hours. The city concept that apply a solution to intermediate level is the first one is abstraction, focus on total hours, not study order. The next one is decomposition, which is break 12 hours into daily allocations. And the last one is algorithm design, work from end goal to daily plan.
Advanced level heuristic question. Optimizing a delivery route. For our advanced example, let's imagine we are helping a delivery person who must visit three locations, A, B, and C, before returning home. The goal is to find the shortest possible route. This is a real-world version of the famous traveling salesman problem.
The first heuristic is solve a simpler problem. The first step is we have to simplify the problem. Treat it as a traveling salesman problem with 4 points, which is H, A, B, and C. Next step is list all possible routes starting and ending at H. So you can see all the possible routes down there. The next step is we have to calculate the distances or the routes that we list earlier. Then we have to analyze and compare. So we got the shortest route is 14 kilometer, which is H to A to B to C to H and H to C to B to A and to H. The pattern is both use the shortest internal link, which is B to C equals to 2. So the final answer is the shortest route is 14 kilometer. The distances is the 14 kilometer. The advanced city concept that applied in solution 1 is decomposition, breaking the route into segments, and then abstraction, ignoring time or traffic, and focusing more on distance. The next one is pattern recognition, noticing symmetry in shortest routes, which is A, B, C versus C to B to A. And the last one is algorithm design, which is systematically listing and calculating all the routes. The second heuristic is logical reasoning. The first step is we have to understand the problem. We need a cycle. We should start with H and continue in any order and ending with H also. And minimizing the distance. The next step is we have to reason logically. The shortest internal link is B to C, which is 2 kilometers. So prioritize routes using it. The next step is test routes with B to C. So for example, we test the route H to A to B to C to H, and the total distances is we got 14, and we reverse it. Also, we got the 14 kilometer. The next step is we have to compare others. We should avoid longer links like A to C, which is 6 kilometer, because like the routes H to A to C to B to H, the total distances we got 20 kilometer. So we concluded the routes with B to C are shortest due to minimal internal distance. So the final answer is the shortest route is the distances with 14 kilometers. The advanced city concept that applied in solution 2 is decomposition, breaking the route into segments, abstraction, focus on distances, not delivery details, pattern recognition, shortest routes use B to C, and algorithm design. Reason 2, prioritize shortest routes.
The conclusion is heuristic construction plays a pivotal role in computational thinking by enabling efficient problem-solving techniques. While heuristic may not always guarantee optimal solutions, they provide practical methods for tackling complex problems in real-world scenarios. The application of heuristic in diverse fields underscores their significance in decision-making and optimization processes. So the essential question is, how does computational thinking skills and heuristics able to produce a superior teacher? City and heuristics equip teachers with tools to design structured, engaging lessons that foster problem-solving skills in students. In the study schedule problem, I use words and trial and error to allocate study hours, demonstrating how teachers can model planning and adaptability. A superior teacher uses cities abstraction, focuses on hours, not content, and algorithm design, iterative scheduling to create flexible lesson plans. Heuristics like trial and error encourage reflective teaching, adjusting methods based on student needs. By mastering these skills, teachers inspire critical thinking, preparing students for complex challenges. Connection to work. The study schedule problem showcases a teacher's ability to plan efficiently. The skill I can apply in my future classroom to balance curriculum demands. So this is the references that I use in this presentation.